First of all, this is a fully connected graph of a dodecahedron, and that's this shape right here, a dodecahedron. It has 12 faces, 30 vertices, and I think 20 edges, or 30 edges and 20 vertices. It doesn't really matter for right now, but this, I tried to create a fully connected graph of a dodecahedron using tiny, thin aluminum rods, but it didn't work out too well. So what I was planning on doing, the possibility is to get elastic string and hot glue to each vertices, each of the vertices, and the end of the string, and pull it tight to all the other vertices to make it fully connected, to make each string connect to each vertex inside this dodecahedron. And I have an icosahedron over here on the desk that I'm trying to do the same thing to. If I can find a hot glue gun that can fit into these models, these terrariums. But what interests me most about this connected graph, what I mean by connected graph is that every single node, every single vertex on this dodecahedron has a line connected into every single other vertex within this dodecahedron. And what interests me are the straight lines, the straight line parallel to each other. Some instances you may have a straight line. These look fairly straight, parallel to each other. Right here, four of them. And over here, this is a straight line. Somewhere in here, there's a straight line parallel to that one. Over here, there's a straight line. And over here, a straight line. And then you might have three straight lines parallel to each other. And what I'm trying to discern with this flat image is the three-dimensional structure of this, of all these lines, of all these parallel lines going through this 3D structure. And that's why I need a 3D physical representation where I can analyze it better, because this is only a 2D representation of a three-dimensional object. And it's kind of hard to get behind there and see where the lines, which lines go to where. And I almost have to outline this in black to and outline the whole structure to actually see where these nodes are front and back and everything. But all of this has to do with my invisibility and holodeck theories, because this takes place. This is a study of the interface and all of these ideas of mine concerning invisibility and holodecks. And I'll go into this. This is, and I call this an invisible cube with a light interface system. It's a light interface system, three-dimensional perspective, and it has a holodeck inside. This is the light coming through the 3D pictures into the wiring harness, optical wiring harness, through into the hollow cavity of the interface itself. Another cube coming back out, and as it's making the invisible effect around the boundary of the cube, it creates a holodeck at the biclock. And this is only an illustration. I've never been able to really do these precise, and that's what the reason I'm taking these sheets of dodecahedron printouts and drawing from vertices to vertices of a fully connected graph to study them in 3D precisely. This was just an illustration. This is how I've worked with all my life, most all my life, on a flat cross-section of a shape within a shape, a polygon within a polygon, polygon within a polygon, and I studied the light going in and the connections between each and every single node, if you consider the 3D pixels, nodes. One connects to every single other one. It completes the line of light going in and coming out. It creates a holodeck byproduct. Naturally occurring byproduct of light interface approach. It creates a holodeck inside. So I'll start with the basics of this. I call these fractal points and fractal lines, and they're what I consider the dual building blocks of all other dimensions and all other intersections of reality. You have a point which you can call a node in a graph. 2 points make up a line. 3 points make up a triangle, polygon, first polygon. 4 points makes up a square. Second polygon, pentagon is a third polygon. A hexagon is a fourth polygon. I'm not sure what 7. I'm not sure what the 7-sided polygon is, but that's the 7-sided. And the one I'm going to be talking about, the one that I'm always true, is the 8-sided octagon. And it goes further, and it can go infinitely further. And the math that I discovered off of this is, well, first of all, you have off-center lines come through off-center. 1, 1, 1, 1. Put ones on these stable. That means it doesn't oscillate like this does. And it has an off-center stable. Then you have 1, 2, 1, 2, 1, 2. Where the line comes through parallel, 2 parallel, and a single, and 2 parallel, and a single, and 2 parallel, and a single. Then you have off-center again, and off-center means open space right here, and stable, 2, 2, 2, 2, 2. Goes on like that. What I added to this was the math behind it. Alternating open and closed webs grow smaller as a polygon approximates a circle. Constant numbers use division. Alternating numbers use subtraction. What I mean by that is this off-center open triangle. You have 1, 1, 1, 1, 1, 1. That's 6 ones. 1 divides into 6 times. You divide that by 2 to get the actual number of lines going through here. 2 goes into 6 3 times. That's a constant number, 1, 1, 1. And this is a alternating number, so you use subtraction. And you add these numbers up. There's 4 2s, you add them up to be 8. And there's 4 1s. These lines, in these directions, you add them up to be 4. You subtract and you get 4, so there's 4 different line fronts going through here. 4 different single line fronts. It goes like that and it keeps on continuously. You can do this for yourself and see the math and see how I get over this math from these fractal points and lines. And here's another image of a fractal point that I'm working with 3, 4, 3, 4, 3, 4. And then finally, this is another image of the fractal point 3, 4, 3, 4, 3, 4. And they all do this. And I just want to see if that also occurs. A repeating pattern occurs on a 3-dimensional intersection of lines. This is a 2-dimensional intersection. This would be a 3-dimensional intersection. And it applies to structures like this.